Today, we're going to try to pull back the curtain a bit on malloc and see what it's actually doing under the hood, because it's kind of interesting and occasionally weird. Hey, welcome back everybody. Today we're looking at memory allocators again. Specifically today, I thought it would be cool to make a tool for one of my classes that helps my students visualize, like actually see what their allocator is doing. So that's what we're gonna do today. But before I get into it, I just wanna say a big thank you to all of you who support this channel on Patreon. I couldn't do what I do without you. You know who you are and you're awesome, and I really appreciate it, so thank you. Also, if you're new, Patreon's where you can get access to all the source code for my videos and my virtual office hours. So if you're interested in that sort of thing, that's where you can find it. Okay, so back to memory, because memory allocators are one of those things. They're really cool, they're really useful. Just about everybody uses them. And a lot of people, probably most people, haven't really given much thought to how they actually work. And maybe you're saying to yourself, oh, I understand malloc and free are those friendly little functions that I request memory and they give me back pointers. And that's right, but how do they work? What do they actually do under the hood? And also, yes, I know about calloc and realloc, and if you're in C++, you got new and delete. And if you're working with other languages, you have other layers on top of malloc and free. For simplicity today, I'm gonna focus on malloc and free because that's typically the bottom where everything ends up anyway. So that's what we're gonna focus on for time and simplicity. I don't wanna overcomplicate this. I wanna just focus on the basics. And the problem I'm trying to address is just that new programmers basically get into this mode where they request memory, they're mallocing a bunch of bytes, but they don't really think about where that memory actually is and how it got there. And on the flip side, maybe somebody like me drew something for you like this that shows you, hey, this is how memory is laid out for a particular process. This graphic has shown up in a few of my videos, and I've pointed out that there's a heap right there, right above the code and your global variables, but a long way below your stack. So that's the heap. But have you ever actually looked at the addresses that malloc gives you? And I'm sure that a few of you have, but I'm guessing that most of you have not. So today we're gonna change that, we're gonna take a look at it. And like I said earlier, look is the keyword. I wanna visualize what malloc's doing. So rather than just tell you what I'm gonna do, let's just jump into the code and take a look. So for this example, what we're gonna do is we're gonna replace malloc and free. Now I've done this in previous videos for debug reasons. Today we're gonna do it for visualization reasons. So this allocator.c file right here is going to be my new allocator. And let's just start off, as we have in previous videos, by creating a malloc function. This is just like the system's malloc as far as what it takes. So it's going to take in a size t, which is a size, and it's going to return a void pointer. And then we also need a free. That doesn't return anything, but we pass in a pointer that we want to free. So that's a pointer that presumably is either null or it's one that we received from malloc, which could give us null. But so these are going to become my new malloc and free functions. And I don't really want to recreate my own allocator here from scratch. I just want to watch it. So for now, what we're going to do, we're going to assume that, for example, malloc has, let's say, some kind of function, we'll call it sysmalloc. We're going to call that's going to be the original malloc. We're going to call that with our size, and it's going to return a void pointer, and then we're just going to return that result. Okay, so we're just basically using our new malloc as a pass-through because we just want to observe. Okay, and we're going to do something very similar with free. We're just going to call some kind of sysfree function with our pointer, and that's going to call the system's free function. Now, of course, at this point, sysmalloc and sysfree don't actually exist. So let's move back up here to the top, and let's make a couple of type defs. So I'm going to type def what I'm going to call malloc-like function. So malloc-like function. This is just going to make my code a little more readable. I've talked about type defing function pointers in the past, but basically this is just going to be a new type, which is a pointer to a function that looks like malloc, one that takes a size underscore t and returns a void pointer. Okay, and we'll do something very similar for free, only it's not going to return anything, and it's going to take a void pointer. And now that we have these types, let's come down here and define a malloc-like function called sysmalloc. I'm going to set that to be null, and we're going to do the same thing with free. We want a free-like function that's going to be sysfree. So the type defs here just make things a little more readable. So now we have these functions, we could call them, but right now they're set to null. So if we call them, bad things are going to happen. Just a word to the wise, don't ever call a null function pointer. Things will definitely end badly. So we need to initialize each of these pointers so we can actually use them. Now I could do this initialization down in malloc and free every time, like right here, I could just use DLSim to go grab this, but I'd rather not do that because it's going to be slow, and it's also for other reasons because we're going to be actually recording our mallocs and frees. It is going to be useful to only do our initialization once. So what I'm going to do is come in here and make another variable here, a boolean called init. We'll start it out as false. And then I'm going to come down here and make a function called init check. And this function is going to be really simple. All it's going to do is check to see if we have not initialized things. And if we've not initialized them, then I am going to now call DLSim. So I'm going to set sysmalloc equal to, cast it to a malloc-like function. And I'm going to call DLSim. I've used this in the past, just it helps me grab a symbol from a dynamically loaded library. In this case, I'm going to say RTLD next. It's going to say, don't get the first occurrence because that's actually the malloc in this translation unit, but get the next one. So that's, and get the next one called malloc. Okay, so we're going to do the same thing with free. So sysfree and free, and we want our free-like function, okay? So this is going to grab the function pointers from libc for malloc and free. And then after this, I want to set init equals true. So that means it's only going to do this the first time, and then init's going to be true. And after that, this init check function will never do it again. And then down here in malloc, I can just call init check, and we'll do the same thing in free. And so now we should be good to go. Okay, so now this allocator should work if I compile a program with it, but it's not going to really do anything interesting yet. All it's going to do is to call the system allocator, system malloc, system free. And what I'd like to do differently is I'd like to actually create a log. I want to produce a log of every malloc and free operation that this allocator actually does. And so I'm going to do this with a file. Now I could write this to standard out or standard error, but I might want to compile this allocator with a program that has its own output someday. And so in this case, I want to use a file so it kind of gets out of the way. So to make this happen, let's come up here and let's create two new variables. So this one, I'm going to make it a file pointer, also start it out as null. And let's also make a character pointer. We'll call it log file name. And I could find a more flexible way to do this. In this example, just for simplicity today, I'm going to hard code it and call this alex.log. Now we can come down here in our init check and just a couple other things we want to do. We want to say fp equals fopen log file name. We'll open it in write mode. So this is going to be the file that we're going to write to. And then once we have that file opened, which that's going to happen at the beginning, then we're going to come down here and we're simply just going to have an fprintf that's going to print to our open file handle. And I'm going to print out an M for malloc. And then we're going to print out a couple of long unsigns, LU. And then this is going to be, the first one's going to be a untptrt. I'm just casting, this is going to be the actual address. It's going to be the numerical representation, the integer representation of the result address that malloc returns. And then we're going to get the size. Okay, so this is going to print out M, comma, the address in decimal, comma, and then the size of the block. And then we're going to do something similar to this in free down here. We're going to, instead of M, we're going to say F for free. And in this case, I only want one of these, and it's going to be the thing that we're trying to free. So that's P, okay? Okay, so now at this point, my allocator should do what I need it to do. And that is specifically, as I mentioned before, that the point is to give you a log of all of our mallocs and frees, and then I'm going to use another program to visualize what this actually looks like. And you might be wondering why I'm using a different program. Why don't I just do it all in the same program? And that would get a little tricky. You know, I could use something like GTK Plus or ncurses. You've seen those in other videos of mine. But those libraries, they also call malloc and free, and that would make my visualizings a little bit messier because I would be visualizing what the visualization is doing as well as my own program. And I really wanted to keep things simple today. I want to keep things isolated. related, so I want to handle these in separate processes. But before I get to drawing, let me just show you a couple different programs. These are basically just test programs that I've produced that are going to create different patterns of allocation. The first one is this batch alloc. Okay, so I've got like a number of iterations and a batch size, and I've got sizes. I'm basically going to try to allocate blocks between 50 and 500 bytes. And then all I'm going to do is I'm going to use SRAN to set up my random number generator. And then what I'm going to do, I've got a batch of pointers, and I'm going to go through, and each time I'm going to allocate a bunch of randomly sized blocks and then free them all. Okay, so I'm going to allocate the blocks, free them all. Just to make things interesting, I'm freeing them in reverse order, but I don't need to do that. In fact, maybe to start off with, we won't do them in reverse order. We'll just keep them going straight. That's fine. So this, we should see a bunch of blocks appear and then a bunch of blocks disappear, and we'll see where malloc puts them. The next one I'm going to look at is random alloc. So random alloc is basically doing something similar, except it's going to do random. So it's, in this case, I've got a struct, which is keeping track of each allocation. That's a pointer to each block that I'm allocating, and the size, which I actually don't actually need. I thought I was going to use that, but ended up not needing it. So we've got our block, and we've got whether it's valid or not, which I could have just set it to null, but anyway, we're using a Boolean at this point. It's fine. We're still allocating blocks between 50 and 500, and we're going to go through this loop a bunch of times, right? This is just so I can see what happens over time, and 500 is going to be the number of allocations that I have at one time. So at any given time, I could have as many as 500 allocations, but I'm never going to go more than that. So things shouldn't grow infinitely. They should just basically, I should have a certain size, and then that should just fluctuate. I'll see things be allocated or deallocated. And so you see that here, this function do lots of allocations. All this is going to do is it makes an array of these structs. So that's not going to be on the heap, that's going to be on the stack. And initially we'll go through in this for loop and set up all of our objects to be false. So no allocations. We haven't allocated anything yet. And then we're going to go through, and our num iterations, we're going to go through each of these, and I'm going to pick a block. Okay, so this RIDX, I'm basically just saying, pick me a random number between 0 and max objects -1. So that's going to be somewhere in this allocs array. And then I'm also going to pick a random size. This is going to be between min size and max size. And then down here, I'm going to check to see if the block I picked at random was valid. Then I'm going to free that block and set its valid flag to false. And otherwise, I'm going to malloc a block of random size. I removed this because I don't really need the size. But so the point is initially we should do a lot of mallocs because most of our blocks are going to be invalid. But then later on, we're going to start to have about a 50-50 shot of mallocing something or freeing something depending on what we've got in our array. And then down here in main, all I'm doing is initializing my random number generator and then calling this function. So really nothing crazy there. So that's number 2. Number 3, my number 3 test function is this leaky alec.c. All it's going to do is initialize the random number generator. There's a pattern forming here. I am doing things randomly. And then we're going to go through a bunch of iterations and call a leaky function. And that leaky function, basically all it's going to do is it's going to malloc 3 blocks and it's going to free 2 of them. Okay, so it forgets to free one of them, and it's just going to do this over and over again. And that's a vestige of a previous example. So up here, just have a couple of constants. So the constants are how many iterations. At this point, we're going to go through and do this 500 times, but we could make it bigger like the others. And we don't need a batch size anymore. You can tell I copied this from the previous one. So we've got our number of iterations and our max size and our min size. Also at this point, I'll point out that I am using a makefile. The makefile is really straightforward. It will just compile all of these different test programs with my allocator. So this should look pretty straightforward. It's pretty typical with what I use typically in my other videos. So now at this point, I should be able to come down and compile everything. It looks like I've got a couple of warnings. Let's fix those really quick. Oops, I messed this up in my attempt to figure this out. Nope, I meant to put J right there. Thank you, compiler, for giving me that very helpful warning. And then what is going on down here? So this warning is in my Leaky Alec, and this is basically just pointing out that that my free here, I'm never doing anything with P2. I'm not really doing much with P1 and P3, but I am freeing them. And so this would be a way to let me know, but we're just going to ignore that warning for right now because it's going to be useful. So yeah, so now we have everything compiled, we have our programs in place, and if I come in here and I run my batch alloc program, you can see that it does in fact produce this alex.log. So my allocator is working, I get this big batch of basically malloc, address, and size. And then if we come down here, you can see that we also free all of these blocks just in the same order that we allocated them. And of course, that's going to work for, let's just look at the others really quick. So if I run Leaky Alec, you can see you get a different pattern. So you're getting 3 mallocs, 2 frees, and they match up. So you can see that I got, these are my 2 frees, and they do match up with these 2 blocks that I allocated. And then if we come down here and look at random alloc, well, you can see now something that, surprise, surprise, is more random and is pretty much the way that I described it early on, mostly mallocs. As we get going, you do start to get more frees mixed in and it gets way more balanced. Okay, so great, we've got these logs and we could look at these, but that's not fun. So let's actually draw what's going on here. And to do this, I've written a little program in Ruby. This is mapper.rb. I'm using Ruby because it was just faster for me to get it working. I'm using the Ruby 2D library, which is super useful, simplifies things a lot. And this program basically is just going to take my log file, it reads it in, and then it draws the mallocs as colored rectangles, and each of those rectangles then get removed when that block is freed. Now, due to time, I am not going to go through all of this Ruby code. There's actually not that much of it, so we could do that in a future video. Let me know if you're interested down in the comments, and maybe we'll do a Ruby video, a little break from our normal C and C++ videos if there's sufficient interest. But for today's video, I really want to focus on these visualizations and actually look at what this produces. So let's take a look. Let's say that I run my batch alloc, and then immediately after, I'm going to run my mapper.rb. And what this is going to do, it's going to pop up this animation. And basically you're seeing, this block gets allocated and then it gets freed. And so you can kind of see how this is working. One thing that you want to notice is that the colors are random just so that you can see the different blocks. Okay, one thing I will point out also is that these blocks aren't right on top of each other. There are little gaps. That's probably because the allocator is saving a little bit of space. And that space is going to help the allocator keep track of what's next and what sizes things are. If we wanted to fully understand what's going on, we'd have to look at the code. We'll save that for another video. But this shows us, we can see the batch basically being allocated and then freed. You do notice every once in a while we get something weird. Something gets placed someplace that we don't expect it, not sequentially. And so again, we'd have to look at the code to figure out what exactly is going on. But for the most part, things are being laid out fairly sequentially. And a part of that is because we're allocating these big blocks and then we're freeing them all together. So that kind of frees up the whole heap. And so then we start back over. And so it's going to start back at the beginning. Also note that usually when we talk about the heap, we're talking about the heap growing up. But for this animation, I'm starting with the heap growing down. So basically at the top is when your small addresses are, and then larger addresses are further down. Also, each row here is a 4K page in memory. Okay, so 4 kilobytes, that's the typical size chunk of memory that we deal with on our modern computers. And so in this case, each row is a 4K page. And so you can kind of get an idea for how many pages I'm using at any given time. Okay, so let's close this out and let's try another one. If I come in here and let's look at my Leaky Alec, we can run that. This is going to run very similarly, or only you're seeing a different pattern, right? So in this case, you're allocating 3 and freeing 2. But what you do see is as this thing grows, basically it's going to grow forever because every time through this loop, it's leaving a block that's leaked, right? It leaks a block. And this just shows you sort of what happens with memory leaks is you're leaving stuff behind. That forces the allocator to come in here and to keep building on to where it left off. And so now I'm using a lot more memory over time. And if I run this long enough, I will consume way too much memory. And this will actually start to slow my machine down. Okay, so let's go try our third one. So if I come down here and I try my random alloc, now you're gonna see very similar, except that now we are basically doing it randomly. And so you're gonna see at some point, we're gonna get to a particular size where we have a certain number of blocks. And then we're just gonna be randomly mallocing and freeing our blocks. And so you just sort of see these popping in and out. Now you notice that the allocator is trying to put my new block requests in the gaps that are left by free. Sometimes it can't fit, right? So we do end up with sort of this fragmentation happening where you get little gaps of memory, of unused memory. And, that's part of what this allocator is trying to do. It's trying to be space efficient, but it's also trying to be fast. And so in the interest of time, it's not always going to be able to take all the time to find the most perfect fit. So it's going to do the best it can. Now, one thing that's really interesting as we look at this, as I've been playing with these, and I don't know if it's going to do it with this example, but occasionally I get kind of weird behaviors. Like you can see that the allocator is actually starting to leave some good sized blocks up here at the beginning. And that's kind of strange. I'm not sure why it's doing that. Probably a speed optimization. But one thing that you will notice if you watch enough of these simulations occasionally is occasionally with this example, the allocator just decides to go off and do its own thing and basically abandon its previously used memory and move on to pages that are further in the address space. Now I'm going to let it run for a little bit and see if we can make this happen. It's been running for quite a while. Also, some of you may recognize this color scheme. Let me know down in the comments if you do. But so right here, you can see what I was talking about. Is right here is like something clicked in the allocator and it just decided, you know what, I don't want to keep reusing these pages I've been reusing, and I'm going to start using further pages, and it starts abandoning. You see these blocks start to get removed as they're freed, and when they're reallocated further down in memory. I'm honestly not really sure why the allocator is doing this. If anyone has any insights, and maybe at some point we'll take a look in a future video and look at the actual code and see if we can answer this question. It might be kind of interesting. But for right now, we're just going to leave that as this is pretty weird. So anyway, I hope this helps you understand a little better what malloc and free are doing under the hood. If nothing else, I hope it's just an interesting visualization and a thought about how you can visualize some things that otherwise maybe seem a little bit arcane, a little bit opaque, and a little mysterious. As I mentioned before, if we really wanted to understand what malloc and free are doing under the hood, we'd have to take a look at the code and try to understand what algorithms they're actually using. And these algorithms may differ from one machine to the other. You know, I'm trying this out on my Mac right now, but if I were to move to Linux or something else, I might see totally different patterns. So maybe we'll look at that in a future video, but I hope you learned something new today. If you did, please consider liking this video or subscribing so you don't miss future content. Also, if you really like the way I teach or the way that we do things on this channel, consider checking out my online courses. I currently have one that is Course Zero. I've got some more that are in the works. I've talked about Course Zero in past videos, and basically it focuses on strategy. Its whole goal is to help you to go from beginner to expert or intermediate or much more seasoned developer who gets paid to do really great work in a short amount of time. So really helping you acquire skills quickly and efficiently so you make the most of your time and effort. So please check that out if it sounds useful to you. And until next week, I'll see you later.